All right, I'm AK 1340, so I'm going to get started. My name is Ian Cooper. For those of you who don't know me, my socials, it's just iCooper on X or Hachyderm. Interestingly enough, you can also find some tech content from me on LinkedIn. Who knew that LinkedIn would become a tech conversation platform with the death of Twitter? But there you go. But either any of those locations, you'll probably find useful stuff from me. Hachyderm or LinkedIn is mostly where I post content. I just get into fights on Twitter. I've been doing this a long time, and there is grey in my beard. I've been doing it a lot of places. We've got a lot to cover. I won't dwell on this. I work on an open source messaging framework for .NET space. I assume most of you are .NET developers and not, say, Java developers you just thought would see how it worked for .NET developers. But yeah, we're an alternative to kind of mass transit and service bus, etc. We try and be good for ASP.NET developers in terms of how we work. We are opinionated about having things like what we call a single-threaded reactor, stuff that may make no sense to you, but do come and check us out. All right, and we just bought Kafka, by the way, on Brighter. Okay, we'll talk about Kafka. We'll have a little bit of a talk after we do an introduction to Kafka and show you how we do basic producing and consuming to Kafka, sending and receiving, if you like, from .NET. We'll dig a little bit under the hood in Kafka, learn a little bit about what makes it a reliable broker, and then we'll do some work to understand how we avail ourselves of those features from C# when we're writing our producers and consumers. We will touch lightly, because we have time, on serializers, deserializers, and the schema registry. We probably won't get into streams and queues. That's probably not really on our agenda today, but I may talk about it if we do have time. All right, Kafka. Okay. So Kafka was created at LinkedIn in 2011 by Jay Krebs, Naya Narkady, and Jim Rao. They are now essentially the leadership of Confluent, the company that effectively evolved out of Kafka, and it's been an Apache OSS project since about October 2012. The reason they built it was that at LinkedIn, they had data coming from innumerable sources, different databases, and they wanted to collect it all into a data warehouse. So it was originally a data engineering project. And they looked at all this diversity of techniques they had for doing stuff and said, there must be a better way to do this in some way that is common and reliable. And the result was Kafka. So what is Kafka? So this basically thing that sits in the middle on Kafka, I can't really use the pointer on that one, there you go, is effectively an append-only log, sometimes called a commit log. So a producer that has some data writes essentially appends to the log, and any readers who effectively want to consume that data read from the other end of the log. Right? And so you just keep reading until you run out of things that have been written, and that is effectively a very efficient way of communicating data. Because we are both the reader and writer can be disconnected in time, in other words, the producer and consumer don't both need to be present at the same time to communicate, they just need the presence of the log, then that conversation can be asynchronous. Right. So I can write to the log and keep writing to the log all the data that I have, and you eventually, even hours later, could come along and read it. Right. So that enables asynchronous conversations to occur between producers and consumers. Typically, we often think about that as messaging. Right? It's a very different way of doing messaging to a queue, which you might be used to from things like RabbitMQ, SQS, Azure Service Bus, right? Because effectively, you are talking about a log that we commit to. It's very fast. It has quite low latency because of the benefits of using this kind of append-only log, right? So what happens with your producer? So your producer will write a record to that log. So the record consists of a key, which identifies that particular record, and the value, the data that you want to essentially write to the log to exchange with somebody else. Your producer gets a TCP IP connection, connects to the Kafka cluster, and says, I would like to write this record. And it writes it to a topic. So a topic is just a named, addressable log. right? So rather than talking about log P13794, whatever, etc., we just say, I want to talk to the order created topic, or I want to talk to the restaurant onboarded topic. Right. So you write to that topic, and essentially the producer appends records into that topic. A consumer then reads from that topic. So the consumer says, hey, I'm interested in orders being created. I will start reading from that topic, and it reads from the other end. Now, when a consumer reads an item from the topic, it doesn't, as you might expect from, say, queuing technologies and messaging, it doesn't delete that item. It simply says, I've read that particular item, so I will record that I've read item number 1. Right? And then it reads item number 2, and it says, I've read that item, so I will record that I've read item number 2, item number 3, item number 4, item number 5. So as it reads to the log, it just records how far into the log it has read. In other words, the index of the last item that's read. We actually say offset in Kafka terms rather than index, but you can think of it the same way. There's a special topic inside Kafka underscore consumer offsets. And what happens is your consumer records where did I read up to in there. That means if your consumer crashes, when you restart it, it goes, now where was I? Oh yeah, I read item number 6. Okay, I'll start reading an item number 7. Okay. And that way you progress through the log. So producer writes basically to the log, consumer reads from the log. Every new consumer starts reading the log at item number 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So the question may become, hang on a minute. If I am writing 1 million items to this log, how is the consumer going to move fast enough for me? Because if I add more consumers, they're all starting at 0, they're never going to catch up, right? So how does that work? So we lied to you a little bit. My topic consists of a number of partitions. It'll have at least one partition, right? But you can have any number more. Each partition is essentially a separate log that slices up all that data we're writing to the topic into a number of individual slices, right? These partitions. So I take my record with my value and my key, and I say effectively, okay, I need to assign this record to one of the partitions. I could choose to do that, and Kafka allows that randomly. I just want you to try and evenly distribute these records amongst all of the partitions that I've created. Or, more commonly, we say that doesn't work for me because I care about the sequence these items are in. Now, think about that original scenario. I'm doing data engineering. I may have effectively be wanting to capture updates to a database table. So I want you to basically see those in order that they happened. Put them in the wrong order, obviously you may get the wrong phone number and address, right? So typically Kafka's used in scenarios where I want to read what happened in a sequential way. Now, if I just randomly write those to new partitions, they're going to be out of sequence in each individual partition to each other. So what I want is, for the same key, write it to the same partition, right? So imagine I'm observing the changes to a restaurant. That's because I work at Just Eat Takeaway right now. And it's restaurant 123. I would like all the changes for restaurant 123 to go to partition 0. All the changes to restaurant 125 can go to partition 1. And then as long as they're in sequence on that partition, I'm going to be okay. We'll see consumers in a second, all right? And that's a technique called consistent hashing. So consistent hashing says whatever your key is, we'll continue to write it to the same partition, all right? Okay. So your producer asks the broker and says, okay, where is effectively the partition that I need to write to? So then your consumers are actually reading a partition on a topic, and the offset they record is how far they are into that partition on a topic. Now, in the kind of default case, when you're just playing around with Kafka and you tell Kafka to create topics automatically for you, you get one partition, right? So your single consumer effectively just says, I'm reading this only partition there is, right? But generally, in production environments, you want to figure out how many partitions you need. We'll come back to that. But generally, therefore, your topics are split up amongst your consumers. All right, so here I'm showing I've got 3 partitions. If I have one consumer, it'll read all 3 partitions, and it'll record its offset into any one of those partitions. If I have 2 consumers, one of them will read from 2 partitions, the other one will read from 1 partition, right? And generally, if I have 3, then each one gets a partition. If I have 4, one of them sits idle. Why might I want that? Well, if one of my consumers goes down, that one that was sitting around doing nothing will now be allocated a partition. And so what happens is Kafka will reallocate partitions to your consumers to make sure that all of the partitions are being read, but only being read by a single consumer, so that you read the elements of the partition in sequence, right? If you tried to have 2 consumers reading an ordered partition, it would come out of order. So you can't do it. So you have to read them with one thread reading a given partition in order. All right. So what that gives us is then a model that lets us, for a given application, have up to as many consumers as we have partitions. There's an idea called a consumer group. The consumer group says, well, my application and this application over here are different. Both of us want to read all the messages, right? So the consumer group says, this rule is true, the idea that we distribute the partitions amongst the available consumers, and they essentially maintain their offsets into that for a given consumer group. So your application and my application can both read the same topic. We both start at 0 on our relative partitions and work our way through. So think about your app as having a consumer group. Okay. All right, so back to the bigger picture so you can kind of see how it works. My producer writes a record to a topic. The producer puts the data in the value, and it has a key for the record. Typically, I want to see all of the changes for a given key in sequence. So I'll use a methodology called consistent hashing to find to make sure that I write the record to the same partition each time. So assume here like 1, 2, 3, 4 goes to 0, 2, 3 goes to 0, 1, 2, 4 goes to 1, and 1, 2, 5 goes to 2. My consumers on the right-hand side, for a given application, and I've got 2 consumer groups. For the first group, I have 2 consumers with 3 partitions. So one of my consumers is reading with just one thread a partition and getting all of them in order. So it's reading all of the changes of 1, 2, 3, for example, in order. The other consumer has 2 partitions, presumably we think they're lower traffic, right? And he's effectively getting 1, 2, 4 and 1, 2, 5 in order and reading all of those. There's another application where essentially they're less interested perhaps in keeping pace, and they're effectively only got 1 consumer and it's reading from all the partitions. And we're recording in the consumer offsets topic how far we have read, so that if we crash, either we or somebody else can take over our responsibility in reading that partition. Hopefully that makes sense, because that's the key to understanding how Kafka works. How many partitions do you need, right? So there is a branch of math called queuing theory. Queuing theory is a bit complicated. I don't understand it. But out on the web, you can find queuing theory calculators. And it works a bit like this. It says there's a rate of arrival of work, right? So let's say your work arrives basically every 10 milliseconds. Okay. And there's a rate at which I can consume work. In other words, there's a rate at which I can do the job of pulling that piece of that item off my stream in Kafka, saying, okay, this is what I need to do, completing that, and then effectively saying, okay, commit the offset for that particular piece of work, move on to the next one. Let's assume that's 20 milliseconds, right? So work is arriving at 10 milliseconds, once every 10 milliseconds, and I'm processing it in 20 milliseconds. If I only have 1 topic, and therefore 1 consumer, I will fall behind. Work is arriving twice as fast as I am reading it, right? So after 20 milliseconds, 2 jobs will have arrived, but I'll only have processed 1, right? After 40 milliseconds, 4 jobs will arrive, I'll only have processed 2. So I will get what's called lag, right? So in other words, that lag is the distance between something arriving and me getting around to servicing it. So what I want to do is say, well, actually, if my work is arriving, if it takes me 20 seconds to process something and it arrives every 10 milliseconds, I'm going to need double the number of consumers, right, to keep pace. Now, that isn't quite perfect. What queuing theory says is actually there's what's called a Poisson distribution of arrival. So actually you need slightly more than that. And the calculator will tell you roughly what you need to do to avoid high levels of latency and waiting. And if that's a bit complicated as an abstract example, imagine going into a shop to buy something, or go to a bar to order a drink. If they have 1 member of bar staff and it's busy, you're going to wait a long time, right? If they have more bar staff than people waiting, then you'll get served quickly. That's really all we're talking about, right? So your partitions are effectively bar staff, if you like, right? You need enough bar staff in order to basically meet the number of people turning up ordering drinks, right? That is the fundamentals of how Kafka works. All right. Running Kafka. This is a horrible Docker Compose file. Running Kafka is a bit of a pain, would be the best way to say it. When I run a workshop earlier in the week, one of the biggest problems we usually get is getting Kafka to run on everyone's machine, right? It's a bit of a black art. Typically, in production environments, a lot of people actually just outsource it. They pay Confluent or Avian or somebody else to actually run their Kafka clusters for them, or even Amazon's MKS, etc., because it is quite a pain, right? Some things you may need to know, though, because you will probably, when you are working locally and trying out Kafka, want to understand roughly what this Docker Compose file, which is typically how I get Kafka running locally for myself, right? How it works. So this is a Docker Compose file that will get you Kafka running on a Mac and a modern Kafka that doesn't use Zookeeper. That will become clear to you later. Okay. So a couple of flags are useful. This one here says basically what should you do if a producer tries to write to a topic that doesn't exist, right? Now, for development, you might just say create it or true, right? Because actually, I don't want to go through all the hell of setting up all my topics when I just want to test something. In a production environment, you never want this to be set to anything other than false because it will give you a single partition topic. Right. So in a production environment, you want to use a different approach to effectively create your topics out of band. Okay. There are 2 things you need to understand: listeners and advertised listeners. Advertised listeners are essentially where external parties, what are the addresses they will be able to communicate with Kafka on, and Kafka listeners is where Kafka is itself listening. Obviously, because you may not be on the same network, that may mean that those may vary. Okay, and at 3.3, it'll tell you about nodes this role plays. Don't worry about that. We will explain that later in the presentation. And again, there's some stuff here which is 3.3 related, which talks about how we run without Zookeeper. Again, we will explain that later. Okay. So once you have Kafka up and running, we will take a look at this in a demo in a little bit, all right? Then essentially, how do you interact with it? So Kafka comes with a suite of CLI tools, and essentially, if you want to set up topics, etc., those tend to be what you use. There is nowadays an API for Kafka. It's a more recent addition as a REST API, so you can also use the REST API to begin to configure elements like topics in Kafka as well. So Bright, which I work on, plugs into the REST API and will let you set up Kafka that way. But typically, in a lot of production environments, you won't want to do that from your producer or consumer, so you'll tend to basically use these tools. So in the bin file, basically, wherever you've installed Kafka, and I always struggle with that because I can never remember on Unix systems whether it's basically var or server or whatever directory. When you finally find where you've installed Kafka, in the bin directory, there are a whole load of command line utilities like Kafka topics, which lets you create or delete topics, console producer, which is basically a simple simple way of just saying, I want to send something to that topic at the command line. And consumer says, I want to read something from the topic from that command line, etc. Get offsets, which will show you partitions and a whole load more, right? So typically, you can set up Kafka using scripting that way. If you want to interact with Kafka as a developer working on an application and understanding what is happening, then a really useful tool is KCAT. And KCAT essentially lets you, is a kind of generic producer and consumer for Kafka that lets you essentially read and write to a given topic, and works nicely with tools like JQ if you want to basically interpret your data, right? And we will have a little demo of those in a second. Oh, now, in fact. I'm going to just show you the UI tools, then I'll do both the demos at the same time, actually. There's also UIs. There's a whole range of them. This one is Kafka UI. We'll show you Kafka UI in a second, and actually probably in a way that's a bit lighter. But there's a whole range of them. AQHK, Kafka Drop, Lenses, CMAC are non-commercial ones. Confluent, basically, and Conductor both make paid-for UIs. You've pretty much got a huge range of choices. Kafka UI is pretty good. This one I'm going to show you. But you get to choose pretty much. And if you're working locally, even the paid UIs are not paid for, if you see what I mean. So just on your own desktop, you could use Confluent if you wanted to quite happily. It just comes out of container. All right, let me do these demos. All right, so I have run this Docker Compose file, which you saw part of for Kafka. It also includes things like the Kafka UI, schema registry, etc. There's a repo I'll give you a link to at the end. You can find all the code that's basically being here in VS Code. All right. So what we're going to do is that's the UI, by the way, I'm just flicking across it. We're just going to run a few pieces of script here so you can see some stuff. So what I'm going to do is I am just going to get a terminal on so I'm running basically that Kafka in Docker. I didn't want to show you starting up Docker, didn't feel like it would help it. So I basically shelled into my Kafka broker, and then I can see I can create a topic. So I can create a test topic. So I'm just saying Kafka topics create, if not exists, topic, test topic. How many partitions do I want? Let's have 3. What's the bootstrap server? So the bootstrap server says, what is effectively the address your client can communicate to get metadata? And we'll talk about that a bit more later on, what the metadata is. So it says I've created a topic called test topic for you, Ian. And I can use this Kafka producer to essentially to write a record to test topic, right? And it's saying, what record do you want to write in? And I'm going to write to this, the most boring record in any demo. All right, and then I'm going to say I'm done. Okay, and then in theory, what I should be able to do is then use a consumer to read that. All right. So I can do this and say, console consumer, talk to this bootstrap server. The bootstrap server will tell me where I need to talk to read this topic, test topic, and read it from the beginning, right? And it's telling me there's a record in there called Coops, right? Now, if I was actually producer and consumer at the same time, you could see I would produce, it would then say, okay, I've seen another record, I could keep going, right? Okay. KCAT is kind of similar. So with KCAT, I don't have to be in there actually, I don't think. I can be KCAT from the command line because I've got KCAT installed locally. And I can say, okay, those are all the things I've sent to topic. So you can see I've sent a few things to that topic when I was testing out this demo ahead of time, and KCAT's saying, hey, that's everything if I start from the beginning that I can find. Okay. And I can also write with KCAT. All right. So I can say -P. So you can see -P or -C. So consumer mode or producer mode. So if I'm producer mode, I can do a similar thing. I can say, okay,
let's write another record to that topic. All right. Terminate that. You don't want to end the... Oh yeah, it says that in my notes. Okay. It may not have finished producing that message. It may be saying, I am really slow. Let's just see. Okay, yeah, so too slow on that one. Okay. Right. Don't worry about that. Why won't you stop? Okay, all right. Kafka UI. So you can see Kafka UI has also effectively got that information. Don't worry about transmogrification. You'll see that a bit later. So you can see here is our test topic, right? And you can see that there are a number of partitions. We asked for 3 partitions, remember? We effectively only have the one message. We can go and look at messages, right? We can see name coops, right? Fallback SerDes was used. So essentially it's saying we didn't tell it how to serialize and deserialize to this. And I will talk to you about that. That's the serialization and deserialization topic towards the end. But you can effectively see what's going on here in that model, all right? Okay. Let's get back to the slides. All right. So that is the kind of basics of Kafka. So we looked at what does Kafka look like? Producers, consumers, topic, divided into partitions. It's an append-only commit log, allows asynchronous conversations because both parties don't need to be present. I can write to the log in an entirely different time window from when you read from the log, right? I occasionally explain in the messaging courses, think about that as being WhatsApp as opposed to a phone call, right? It's basically it's a message, right? So we're going to write a little... we're going to use a consistent test example when we're showing you some C# code to show you how that works with this. We're going to build the Calvin and Hobbes transmogrifier. Who's old enough to be a Calvin and Hobbes fan in the audience? Who's never heard of Calvin and Hobbes? Okay, go and read some Calvin and Hobbes. So Calvin is a small boy and Hobbes is tiger, a stuffed animal. Calvin owns a transmogrifier, which is a cardboard box with the word transmogrifier on it and some dials that allow him to change into various creatures, including Hobbes. So we're going to build our own transmogrifier. We will have a CLI that will ask us basically what we want to transform into. We will basically take those settings, we will send it across to a consumer, and the consumer will effectively do the transmogrification for us. It was better than Hello World. Okay. So what does it look like to produce a message in C#? All right. So ignoring the boilerplate at the top, this is the dispatching method. You'll see it in context of the whole code base in a second in VS Code, but let's talk about what we're doing in here. So the first thing we do, we need to create a producer. So in C# we use a producer builder. And notice we're basically giving it a type of string. What does that mean? That means that the key type for this message will be a string and the value type will be a string, right? And we can obviously adjust those to say what do we want the key and the value type to be for whatever the record is we want to create, right? We pass it a producer config. We will show you that a bit later, but essentially that is going to tell us where to find that bootstrap server for Kafka, and then we build a producer. So we say, create one of these producers for us. Then, in order to send a message, we do producer.produce, and we give it the topic. What is the name of the topic we want to send the record to? And the message, or record, effectively, has the same key value type of string, and then we set its contents. So our key is just going to be the name of the setting, and our value is going to be the actual transformation. Then we flush the producer, right? We don't typically do that necessarily per send, but you will want to do that before your application exits. Why? When you call producer produce, effectively what happens is under the hood in your client SDK is it says, great, got that work, I'll queue it up and I'll give it to Kafka. Your program can continue. So in other words, it's a very quick operation to produce, but you now have a buffer which isn't necessarily flushed to Kafka. So flush is important before you exit to make sure all of your
records have been written to Kafka successfully. There is a return value from flush, which tells you how much still needs to be written. So you can actually do that in a while loop. And effectively, I'm not doing that here because I only ever have one message to flush, right? But you can do that in a while loop to basically make sure that there's nothing left to flush out of your buffer from Kafka, right? This does mean that producer.producer is effectively async, right? Because it writes to a buffer and you continue. There are async method support. We'll talk about that a little bit later. Actually, it's slower than using produce. Okay. And at the end, we want to dispose the producer like any resource. So topic we want to write to, there's the producer config. You might better read that. Localhost 9092, any bit we care about. Create a producer, key and value string, produce a message to a topic, right? And tidy up. Okay. How do we consume a message? Tiny bit tiny, isn't it? I'll walk through. You'll see it again in VS Code in a second. Need to take the topic we want to consume to, and we basically need to give it the config again, which basically is, again, the bootstrap server. But also here, we're going to set a little bit of additional information, which is the group ID. Remember, we said you belong to a consumer group, all right? We'll see it again a bit in big in a second. Similarly, we create a consumer from a consumer builder, and it's exactly the same. It's a string that we're reading off, right? A string key and a string value, all right? What we're doing here, and this is just the way I've set it up, is our run method will effectively spin reading from a given stream in Kafka, from a given topic, right? And so there's going to be a while loop in there. What we're actually going to do, because this is typical of kind of messaging frameworks, is pass in two functions. One says, how do I translate between this message on the wire and something a type I might want to be able to use internally, and the other says, I'm going to then handle that message. And you'll see how we do that when we get to the actual code in a second. So we subscribe to the topic, we run the message pump on an endless loop, right? And we say, okay, use a cancellation token to make sure we can exit the loop if we're signaled to, translate the message, handle the message, right, and deal with any errors and tidy up and close. All right, and so we've got in our main method configuring Kafka, and essentially we will tell you here what our methods are that translate and then do actually handle a message. All right, so let's see that code. Which way is that? Okay. So just that producer code, again, to remind ourselves. There is the dispatcher, right? There's that. Is the code up on screen? Let me kill that. Die. All right. Excellent. Okay. So we have our producer. Here is basically the producer build statement, right? Here is basically our producer producing, sending that message, and we flush. All that's happening in terms of the program code is we have some UI, that's just spectre.console. I won't show you that code. Please go and look at the repo if you want to see how that works. And what we're going to say is I'm going to ask you for your name. I'm going to ask you for the transformation. I'm going to tell you what you selected, and then I'm going to essentially, when we do enter transmogrifier, say, do you want to do this? And then we'll send a message via the dispatcher to produce. And then the consumer code, the one that was harder to read, all right. And the message pump, we're going to say, well, build a matching consumer that's string, right? And then subscribe to the given topic, right? Remember, the topic is how we know we're addressing the same commit log. And then we're going to say in a while loop, read from that topic. If effectively we've run out of items to read, in which case yield for a bit and then come back and check again later. Then I want you to translate that message into something useful and then handle it. So you can see in the program file, what we're actually saying is create this message pump and run it. And what we want to do is turn the message into a new transmogrification. Right, and then we'll output the transmogrification that we're going to make. All right. So, oh no, spoilers.
Is that font big enough, or do you want it to be a bit bigger? Big enough? Bit more. Transmogrify is a long word, it turns out. Okay. All right. So, .NET Run, there we go. What's my name? My name is Ian. I'd like to become a tiger. Right. So it says basically, I've entered the transmogrifier and I'll come out as Ian. All right. So if I don't, that's the producer. We can see now. There's a slight thing going on here to just explain. You can see I've got transmogrification. I currently have 21 messages. So I could have done something where before the demo, I deleted the topic and reset all my consumers, etc. But my slight thing then was, how do I know the demo is actually going to work? So let's just assume 21 is now base number of messages, and you'll see it go up. All right. But we are reading effectively, you'll see, from this point. If not, I've got a fix, don't worry. Okay. And we can run the consumer. Begin the transmogrification, and I should want to be transformed into a tiger. And I could do it again, all right? I could run it again and say, Ian, what do you want to be transformed into? This time I could say a frog. Right, and you can see I got a frog. So the consumer is in a loop, and it's just reading the next thing that I write. Okay, fairly straightforward. And that's how you write to Kafka, and we're done. Great, thanks. All right.
All right, just a few more things to tell you about Kafka. So Kafka tends to come in a cluster. Right? One of anything is going to be bad, right? Because I've got a single node there in Docker Compose, which is fine for me running on my machine. But obviously in your production environment, you're going to need multiple nodes, because if you lose that single node, well, you've lost any access to all the data written to a stream. So you have multiple nodes, typically a core at number 3, 5, etc. Right? So any given partition is copied across all those nodes. One of those copies will effectively be the leader, and all writes go to the leader. Okay. Since about, I think it's 2.3, you can read from the leader, but you can read to any of the followers to whom that data is copied. Right? So I write to partition 0's leader, the data is copied to partition 0's 2 followers on broker 1 or broker 2, and essentially, therefore, I can read from any one of those 3 brokers. Notice that for the next partition down, partition 1, the leader is actually on broker 1. So the leaders are distributed across the brokers in order to distribute the right load. In the event that I lose a broker, then what happens is the controller, which is one of the brokers, will redetermine which the leader of the partitions is that you should now write to and the other followers should listen to. All right. The bootstrap server, which you saw in some of that config, all right. So when I connect to Kafka, you don't usually have to do too much, but your SDK is doing quite a lot of work. One of the things it's saying is, I need to know on which broker the leader partition is, because that's what I want to write to for this topic. To find that information, it needs a server to tell it where do all the leaders and followers live. And so the bootstrap server effectively just means that the server you ask for the metadata to tell you where to send your produce requests and where to make your consume requests. Who decides who is basically the controller who determines which of these nodes are going to be leaders and followers? So, obviously, if I've got a leader and some followers, someone's got to make the decision. You're the leader, you're the follower. Especially if a broker goes down, someone's got to say, well, okay, now you're the leader, you're the follower for any given partition. And that is called the controller.
So the controller is basically, in Kafka versions prior to about 3.3, is one of your nodes in the cluster, and its job is to determine which are the leader and follower partitions. Okay. How do we know who is the controller? So this is where Kafka used to have, and you may still find does in some of the instances you're using, have a dependency on Zookeeper. So Zookeeper supports a number of primitives, such as basically consensus algorithms. So Kafka uses it for that. And what happens is, as each Kafka node comes up, it tries to create an ephemeral root node on basically Zookeeper for that Kafka cluster. If it's the first one, it gets to be root. If it's another one, it doesn't get to be root. Right? Root says, I am the controller. If root goes down, because it's an ephemeral node, the node disappears and somebody else grabs root and they become the controller. So that's why there's a dependency you'll see in some Kafka setups for Zookeeper. Since about 3.3, Kafka has not needed Zookeeper anymore to do that, right? So now, essentially, what happens is that the Kafka nodes implement Kafka Raft. So Raft is a distributed consensus protocol, right? Or often called Craft, which makes me think about Dairy Lee cheese because I'm British. And essentially, the individual nodes will decide amongst themselves who gets to be the controller in case one of them effectively dies. Your nodes can either act as brokers, controllers, or both, depending on how you want to configure the resilience in your cluster. Acts. So we mentioned a little bit earlier that when we were writing, we said one of the optimizations Kafka gives you on that producer produces under the hood in the SDK, it's buffering those writes to the producer so your code can move on. The other question really is, when I write to the producer, what do I take as the confirmation that I have successfully written my record? So I could just say, the broker says, hey, yeah, you talked to me, right? And that's what we call Act 0. I don't know whether it's actually been written successfully to any of the nodes in the cluster. I just know that it was acknowledged that it got it. If effectively the node that I was writing to crashed before it wrote it to the leader partition, because that's the node I should be talking to, then effectively that write would be lost. Right? That's Act 0. It's fast in terms of that response back to so you're going to eat through that buffer fast, right? But it's potentially lossy in the event of that node crashing. Act equals 1 says, I should know it's been written to the leader, right? That's a little less fast. Now, I know the leader's got it. So if there's a write, I'm assuming that under the hood, it's going to basically be replicating out to those followers. I don't know, though, that it's not going to crash before it's actually replicated. Now, there's a lesser chance, perhaps, than effectively I'm going to get message loss with Act equals 0, but there's still a chance. Act equals all says, when I write, don't tell me it's done until essentially you have given me information back from all of these, all of the nodes that it's been successfully written. Now I know I'm not going to lose the message. Okay. Now, question you may be asking yourself is, hang on a minute, if the buffer is doing the writes, how do I know whether it achieved any of these things? And we will come back to that. Okay. Kafka determines the health of given nodes by asking itself, how far out of alignment are they with the leader? Right. So this is called lag. It's saying, how far behind in terms of the writes is this replica in terms of what it's basically showing in its copy of the partition, right? And if that number gets too high, in other words, there are 5 or 6 writes that it's not got yet, then essentially what happens is Kafka says that replica is no longer in sync, and it basically takes it out of the cluster. At that point, your writes no longer in an Act equals all consider that a broker they need to write to, and it's not one you tend to read from, right? And typically, you've got to figure out what happened to that particular node that it's dropped out. Okay. So
few things we need to know about writing reliable producers then in C#. There's some configuration things you want to think about. So on the screen here, you can see in the little box when writing our producer topic foo, ax equals all typically means we're going to copy that to all of the nodes in the cluster. That's probably best if we want to be reliable and we can't risk message loss. Retries is how many times the producer is going to keep retrying to send a given message in the buffer before it gives up. Typical values are something like 3, but you may want more if you really can't afford to lose a message. And retry back off says, what's the gap in between each one of those retries to write to the broker? There are typically in a network transient errors, right? Networks go down for a period of time, so essentially you need to work on that. A max in-flight request per connection says, how many threads can you use to basically read from that buffer? If you require strict ordering, keep it at 1 in order to make sure that you are reading the buffer in order. Okay. So if I want to reliably produce a message in C#, a couple of things I might want to think about. So the first thing up there is my configuration, right? Actually, that's saying ax leader, should be ax all, right? But I've got some new elements there. Ax, the maximum number of retries, 3, and the max in flight in that config in the corner. So I need to configure the SDK, and I might want to also make sure I set an error handler in my builder so I can understand when Kafka's telling me things have gone wrong. In order to understand whether Kafka actually successfully wrote my buffered record, I should handle essentially delivery report. So that's a callback and produce, right? So I register a callback and I say, tell me whether it got sent. Now, what am I going to do with that? Right? Because that's coming out of ban. And what am I going to do if it didn't get sent? So the typical strategy in most messaging frameworks is to use an outbox. This is a noddy in-memory outbox. It doesn't really work. Don't go and put this one in your deployment. Right? But what this just says is I'm going to record when I send a message. I'm going to add something to the outbox. You can see that in line 28. Right? I'm going to add something to the outbox. And effectively, when I get the delivery report on 19, I will mark that as seen. Now, in a genuine outbox implementation, what would happen is you would look for work that had not been sent in a given timescale and resend it. Okay. All right. That one's okay, yeah. Async. So if you do use async, right, you can create an async producer. Then what happens is it's just async await, and the report is returned to you as the response to the async await call. Right. So you just handle the returned report value. It will be slower than doing producer.produce, and producer.produce is also effectively async because it doesn't block. Right. Why won't you ever want to use this? Because async is viral, and you may end up needing to basically have an async produce. All right, let's demo that. I don't have time. Die. Right. Oh no, there's even more spoilers. Don't know why I left all these spoilers up. Right, let's look at code first. Okay, just to remind you. So demo number 3. Producer. We will actually be using this dispatcher. You can see we create this action delivery report, right? It's just a callback. And what we're saying is mark the status in the outbox, right? What we've done is that's just a callback. We try and send the message. We put basically it in the outbox, and then we produce it. When we register the handler, and that will call this, which will then mark the item in the outbox. The outbox is not anything other than just a dictionary which contains those values, right? It's not production grade anything, but it lets us interrogate it afterwards. This is what the async dispatcher, we're not using that one, but this is what the async dispatcher looks like. So it's in the code, which I'll give you the GitHub reference at the end, so you can go and see that if you need that for your scenario. And this is the consumer. Right, here's the message pump again. So very similar, we're subscribing, effectively, etc. There's no real change to the consumer in this model, right? We'll come back to store offset later. You'll see that, but we're going to talk about store offset in the next bit of the slide deck. But you'll see a little response. So you can wonder,
What does that mean? What is Ian doing? Is that readable? Needs to be bigger, doesn't it? Big enough? Oh. Oh dear. Let's start that again. Okay. Let's make you bigger as well. Is that visible? Visible? Okay, what's a transformation? Make me an eel. I have to get the case right because my code is not that good. Okay, so I want to be an eel. Can you see I've now got this box marked sent messages, where what I'm saying is that basically that is the contents of the outbox. So it says there's a transmogrification topic. I sent something with the key of E and the value of eel. It went to partition 0. Its status is persisted. In other words, basically, that's the status I got back on the delivery report to say that now exists on all of the nodes in my cluster. There is only one node. All right, and it tells me when that happened. And I can consume that. The nice sort of table effects and stuff are all just spectre.console, by the way. And you can see that code in GitHub. It's not a talk about spectre.console, though, so I don't want to spend too long on that. Okay, so I can say, Ian, I'm going to transform into a baboon, because why not? I'm done. Right, okay, so you can see Ian baboon 0 persisted, and you can see I'm reading those on the other side, all right? All right. How am I doing for time? All right. Oh, I'll just keep going in. No one cares how much time you're wasting. All right. Timing is an issue to cover everything. All right. Transaction reliability. You can try and increase the number of items that you are sending at once. Typically, what you need to do is a couple of things. You will need to enable item potence, and that essentially says, Kafka, do not make sure that you do not send the same message more than once, and you will probably need to use a transaction, which means you need to create a transaction ID. So here is some code that creates a transaction. You can see at the top, it's doing producer init transaction, producer begin transaction. So the init transaction gives me a time span. Begin transaction, you can see at the bottom, it commits, right? Typically also useful if you want to send a cluster of things that have to be sent in order. It will automatically set ax all, max in flight to 5, and max int retries. In other words, it will keep retrying until it finally gives up, right? And if you genuinely have a problem with how the sequencing of your message is going to Kafka, you may need to fall back on those transactions. We're not going to demo that just because of the interest of time. Okay. Reliable consumers. So remember we talked earlier on and said our consumer stores an offset to tell us how far it's read. By default, out of the box, if I do nothing, if you can see up in the top right-hand box, it says enable auto commit equals true and enable auto offset store is true. What that means is this. Enable auto offset store means when I've read a record from the Kafka stream, put in a store that offset has been read. Enable auto commit means every 5 seconds, commit those to the consumer offsets log in Kafka. So the code on the left, which is what we've been running up to now, effectively when it consumes something, stores to the offset log that's read that item, and in the background it will be committed. Okay. But there's a problem. I've consumed it and said I've read it, but what happens if there's an error at translator or handler or my application crashes? I probably don't want to mark that work item as done. I want to be able to come back and do that later on, right? Or if this application just crashes, have something else pick up and take over the work that was otherwise lost. But I've committed the offset, so my consumer doesn't know. So to fix that, I'm going to have to manually take over part of the operation. The simplest model in .NET It's not the same for all Kafka packaging libraries, quite how this works. But in .NET, the simplest model is for us to essentially say, I'll take over storing the offsets. So I will store the offset, essentially, for you whenever I basically hit a number that I have done, right? So I'll say I've translated it, I've handled it, it's done, store the offset. In the background, the SDK will say, okay, I'll commit that offset every 5 seconds. That's the simplest way of doing it. Your only problem is essentially still, if you get a bad crash, you might have pending offsets that you never see, and so effectively you will replay those items, right? Your consumer, when it restarts, will go, hey, we only reached 5, even though you might actually have processed up to about 10. So your other alternative is to say, don't commit for me, don't store offsets, I will choose when to commit for you. Right? And on that model, we actually call commit rather than offset store and tell it a commit has been made. Now, there's a trade-off here. If I'm committing every single time, my problem is going to be that's very chatty, right? They're going to slow me down. So typically at that point, I might want to batch commits. If I batch commits, maybe I should, am I any better off than when I was using a store? Right? Because I could still lose if I crash during the middle of the batch and it's not been committed. So you kind of have to figure out what your tolerance is, whether you're more tolerant to performance issues or whether you're more tolerant to having to maybe replaying some messages when you go missing, right? Something like Brighter, we let you have quite a lot of control. We actually do manual, but then we do batching and we let you make a lot of control over quite how that works. The other thing to bear in mind is that whatever strategy you choose, if you now have taken control of storing offsets or commits, you need to react if the partitions change. Don't forget, effectively, the partitions can be revoked and you can gain and lose offsets. All right. So you typically have to say, whatever my strategy was, I will set up in the partitions revoked handler to store offsets or store commits. All right. Quick demo, because I realize we are difficult on time. Okay. I think it's this one. Yeah. We know the form. Okay. And then if I clear you can see that what I've got there is a note saying I committed this offset, right, to partition 0, offset 24. You've been doing a number of demos. We're about 21 earlier on. You can see we're just advancing the new offset, right? So we're just manually committing offsets at that point. All right, let me stop that. All right, need to go a bit faster. Offset resets. I won't show you this, but there is some code. There's actually some in the sample which will let you reset the offsets for a given topic, etc. Typically, though, the simplest way to do it often is just change your group ID, right? Just change the group to consumer 2. You've got a new group ID. You're effectively going to start from 0, right? Okay. Great trick. Serializes, deserializes in the schema registry. So on a given topic, we can essentially establish that either the key or the value or both may have a given schema. Kafka supports Avro, JSON schema, or protobuf. So we don't have to do everything in terms of strings, right, or other primitives. Okay. Typically, there is a relationship between a Kafka topic or one or more schemas. A lot of complexity. For the minute, let's just assume the simple case, which is there is a schema which has the same name as the topic dash value. Right, that's the default. There are more complex arrangements. Okay. Schemas effectively have a whole list of rules if you wish to enforce them via a thing called the schema registry, which tell you whether or not, when you make a change to that schema, it is backwards or forwards compatible. And this is a big table that Kafka gives you that tells you what that means.
It's complicated. Let's have an easier version. So your choices are really consumers using the new version can read messages using the last version. So the thing you send is still usable if I only know about the last version of the schema. Producers using the new version can send messages to consumers with the last version. In other words, my producer can send a message with the new version, right? But I can still read but the consumers can be on the last version. And full, it means effectively either side can be a version out and it still works. The transitive lines just mean not just last, but all versions, right? So it's to do with compatibility. How do we use that, right? So the idea is that the producer on the left-hand side here says, okay, when I'm going to do a write, I will write and I will check basically the contents of my write against the schema registry. Hopefully, it's in my local cache, so I don't actually have to call the schema registry, which could be down in theory, right? If not, it doesn't exist, I will get it from the server. If it doesn't exist on the server, I can kind of create it and put it in the server as version 1. And I can configure the schema registry to say what kind of compatibility, backwards, forwards, etc., am I enforcing, and it will throw an error if my attempt to produce doesn't match that enforcement. Similarly, when I can consume, although typically we don't tend to do so much enforcement on consume, I could also choose to enforce that the messages I'm receiving match the schema registry. When Kafka writes, when you want to write something that effectively uses the schema registry, the slight wrinkle is that your value has a more complicated format. Kafka basically started to use this before it had the notion of headers for records. Only had a value and a body, had no metadata. So the problem is it needed somewhere to store schema ID. So what it does is it takes the first 5 bytes of your value, it makes the first byte a magic byte, which is the version number of the serialized value. At the minute, it's always been 0. And the next 4 bytes are the schema ID, and the remainder is your data, right? So that means effectively what you need to end up doing is either manipulating the bytes of your value that you're sending to your message, or using one of the Kafka SerDes serializers, or Confluent SerDes serializers. So here, what we're going to do is use the Confluent JSON serializer, which under the hood uses NJSON schema and Newtonsoft JSON, just to make you annoyed, which means that you have to mark up your data for both Newtonsoft and system text JSON if you want both of them, which is really annoying. But it basically, this will say, use the JSON serializer, and that will handle that for you. It will handle magic bytes and everything else, right? Okay. It is also async over async. Why? Because effectively, the JSON serializer is async, but producer.produce is sync, and they have to match. Okay. Schema registry, I will skip that demo just because of time, but you can see the code. It doesn't do anything apart from serialize it using the schema. All right. Okay. We're at the end, so let me just finish some links. All right. So you can find the sample code there. You can run that last demo for yourself. All it will do is output the schema from the schema registry to your command line for you. Brighter is also linked there. We do handle Kafka as a topic. This presentation is a PDF version because I couldn't upload the PowerPoint file. It's too big in my GitHub repo. There are topics we didn't have time to cover. Just a brief mention of them. Kafka Connect. Kafka Connect comes from its data engineering days of Kafka. It's a way of hooking up a data source like a database or another queue to turn it into a Kafka stream, and then effectively do the same at the other end, turn a Kafka stream into a database. Right? KSQL is essentially the idea that if streams are effectively data, I can essentially take a time window, look at the data, and run SQL queries over it. Our experience is it kind of sucks. Streams applications let you actually write applications that use those streams in a more reactive way. There's a standard library for Java. There are some C# ports of that library. right? And there are alternatives to Connect. Even Confluent themselves have switched away from Connect and KSQL to Flink. We really like Benthos. Benthos is a really nice tool. You go and find it at benthos.dev. It's a Go lib, and it is what Kafka Connect should have been. All right. That's the end. I'm sorry I overran slightly, and apologies for schema registry. If anyone wants to hang around, I'll do the schema registry demo, but if you want to go, feel free. All right. Thanks, everybody.